Good morning, beautiful students. Here we are in the sixth week, and we're studying innate immunity in chapter 15 and adaptive immunity in chapter 16. I'm going to record a little bit later on regarding the lab because I know that a lot of you are concerned about the lab. I'm aware that the lab is taking longer than it should, and I have narrowed out the problem to the fact that we're trying to incubate Micrococcus luteus, which is a very slow-growing organism. So a lot of you are concerned that two of your cultures have taken off, but the Micrococcus luteus is not, and nothing's happening. Something's happening. It's just happening slower. And so we're going to have to give it a little bit more time. So don't concern yourself with the Monday due date. I'm going to open it again. We're going to work together to be successful. Okay? So don't worry about that. Let's for now, let's concentrate on what we're doing, which is innate immunity in chapter 15. This is one of my favorite topics. It's incredible the way that our body works. Okay, which is apparently better than my PowerPoint works. Okay, so first line of defense, you should contemplate the skin and the mucosal lining of our body. So our mucosal lining is rich in goblet cells, which secrete mucus, okay? And that mucus serves as an adhesive for things that would normally go into our body that we do not want into our body. So the example that I like to use is a respiratory system. We have a trachea, we have a pharynx that is saturated with pseudostratified ciliated epithelium. And in the middle of this pseudostratified ciliated epithelium, there's these beautiful goblet cells creating mucus. So when we inhale something, those particles get attached to the mucus instead of going into our lungs. And then our ciliated epithelium moves it up and away from our lungs, which are azenic. In other words, they are free of any foreign contamination. And then we do something that sounds disgusting, but it's actually desirable. And that's the fact that we swallow that mucus. And that mucus is going to be rich in foreign matter. It's going to be rich in bacteria. And it goes into our stomach, where our stomach hydrolyzes that bacteria and kills it, and consequently protects our lovely lungs, okay? So these dendritic cells, these goblet cells and that pseudostratified epithelium is very, very useful in keeping us healthy. Another point that's important to remember is these dendritic cells, okay? So dendritic cells are effectively the tissue's version of the monocyte, okay? It is, I call it waste management. It goes out, it goes into tissues, moves among the tissues in an amoeboid motion. And if you don't belong there, it phagocytizes it. In other words, it eats it, it digests it, and then it travels to the lymph nodes via the lymph vessels, and it carries out antigen presentation so that our adaptive immune response knows that X, Y, and Z should not be in our body, and it should be attacked and destroyed. Very, very neat. So these dendritic cells are just below our epithelium, both on our skin. They're also in the mucosa of our digestive system, okay, of our intestines. They're also found in the Peyer's patches of the ascending transverse and descending colon. And these dendritic cells are always just kind of going through the surface, stealing a little bacteria, they're consuming it, and then doing antigen presentation. So if you can imagine that you have all these soldiers protecting you, okay, what better way to keep them prepared than to actually have them attack the enemy, the bacteria, on a daily basis, and be able to sustain that training. Oh, excuse me just a moment. Uh, sorry, I got a little interruption there, but it was by one of my wonderful DE students and data concern, and I think we took care of it. So I don't know. It makes me happy. All right. So anyways, we're talking about goblet cells and pseudostratified ciliated epithelium keeping our lungs clean. And then other things they should remember, of course, is that our tears have lysozymes that destroy gram-positive bacteria. Our skin, the sweat in our skin, makes for lack of a better word, a toxin against bacteria called dermcidin. Okay, and this has been spelled. I don't know why. It should be DERMCIDIN. DA shouldn't be in there. It should be dermcidin. DA makes it sound better, but it's not supposed to be there. And cidin means to kill, of course, and derm means skin. So these are peptides that are released by the sweat glands. It goes on the surface of your skin, and again, what it does is it kills bacteria. So this is beautiful things that happen by your first line of defense, which again is your skin and your surface secretions and your mucosal lining. Okay, let's move on here if I can. All right, now we're moving on to body's second line of defense, which is the innate immune system. And we start with an interesting topic. The topic has to do with the fact that when you have an infection, a lot of the microorganisms are either facultative anaerobes, which means that they can use oxygen, or they're obligate aerobes, okay, which means that they require oxygen. In both instances, they need to have an electron transport system because they're breathing, they're requiring oxygen. And because they have an electron transport chain, that means that they need their cytochromes require rare elements such as sulfur, copper, and iron, okay? Well, where do you get iron in the body? Hemoglobin, okay? So what happens is that in our body, we have this plasma, that's what we're talking about, the body's second line of defense. So we have plasma, which is when you take blood and you centrifuge all the formed elements off of it, you end up with this straw-covered liquid, mostly water, some electrolytes, some oxygen, some nitrogen, some CO2, sugars, proteins, etc. Okay, and one of the things that this plasma carries is this thing called transferrin. So transferrin is a molecule that our body produces to transfer iron from the small intestine to the liver, so it can store it there and make hemoglobin in the future, okay? So we have this transferrin. So what? Well, now if you end up with an infection of, say, Staphylococcus aureus, Staphylococcus aureus produces an iron-binding protein called siderophores. And you should know this, okay? Not only because it's important, but also because you're going to be assessed on it. So it produces these things called siderophores, and these siderophores have a higher affinity for iron than transferrin. So the Staphylococcus aureus literally steals the iron from our body. What does our body do? Our body reacts. It becomes aware of this problem, and our body produces yet another protein called lactoferrin. And this lactoferrin has even a higher affinity for iron than siderophores, which means that our body steals the iron back from these bacteria. Well, you would think that we'd win. Unfortunately, that's not the case. So now these bacteria make hemolysin. And as the name implies, hemolysin is a protein that lyses red blood cells. So now the Staphylococcus aureus has the access to all the iron that it needs, okay? The problem is that you cannot have hemoglobin in the circulatory system, okay? Hemoglobin needs to be contained within the red blood cell. If it is loose in the circulatory system, it causes problems, and in particular to the kidneys. So this causes an issue. But again, this is a topic that I find interesting because it shows the tug of war for a resource between a bacterium and our body. Okay, very, very interesting. Now, Neisseria meningitidis, it actually makes a protein that literally plucks this transferrin from our body and out of the blood. Okay, so this is a common problem. So as you can imagine, somebody who has a systematic infection is going to be suffering some anemia because the infection is literally stealing the iron out of your body. Very incredible stuff. Okay, so let's go back to the second line of defense. We said that we had plasma, which is everything except the formed elements. What are the formed elements? The main part of the formed elements are the red blood cells, the erythrocytes, the clotting part of the body, which is the platelets, and of course the part that we're looking at, which is the white blood cells, the leukocytes. Okay, so this is a good point, and this is a good place to address the things that you should know about white blood cells as a nurse. Okay, and the reason for this is because you're going to be asked about it. Okay. Just because you're not being assessed on all of this in this class doesn't mean that you might not find these questions on a state exam, because this is key, okay? So what do you need to know? Well, you see all this information here? We should start with knowing what it is that each one of these white blood cells go towards or go to destroy, okay? So let's start with basophils. What do basophils do? Well, basophils are mediators of inflammation, okay? Again, we're talking about pain, swelling, redness, and heat at the site, okay? All those signs are the events, the effects of the degranulation of this basophil. Let's go to the neutrophil. What do the neutrophils do? Well, neutrophils typically go on after bacteria. Okay, so that's an easy one to remember. Eosinophils, what do they go after? These usually go again after parasites, helminths, worms. Okay, so that's the eosinophils. Monocytes, this is my waste management. These guys go after everything. If you don't belong in the tissues, a monocyte is going to phagocytize you, is going to break you down, and is going to carry out antigen presentation in order to launch the adaptive immune response. So monocytes go after everything. Lymphocytes, okay, lymphocytes are very complicated. They can turn into natural killer cells, which are part of the innate immune system, which is what we're covering right now. Or they can turn into T and B cells, which are part of the adaptive immune response, okay? So these guys get complicated, and they typically go after cells, body cells that are infected with viruses. So that's what the lymphocyte does. What else should you know? Well, you should be able to distinguish the phagocytes from the non-phagocytes. What does phagocytosis mean? It means those white blood cells that consume their prey, okay? How many phagocytes do we have? We have 3. We have the neutrophil, the eosinophil, and the monocyte. The others are not phagocytes, okay? What other things should you know? You should remember whether they're part of the innate or adaptive immune response. This is not too hard to remember. All of them, without exception, are part of the innate immune system, even the lymphocyte. Why? Because some of them become natural killer cells. However, it is only the lymphocyte that is actually part of the adaptive immune response. So to recap, all of them can be part of the innate immune system, including the lymphocyte, because a lymphocyte can turn into a natural killer cell. The lymphocyte, however, can differentiate into a T or B cell, and when it does that, then it is part of the adaptive immune response. What else should you know? You should know the difference between granulocytes and agranulocytes. So granulocytes means that they have granules. Do we care? Yes, we do. Because if they have granules, those granules are part of the way in which these cells work, which is called degranulation. In other words, When they find their prey, they release these granules, and the granules have the enzymes necessary to carry out their function. So how many granulocytes do we have? Well, basophils, neutrophils, and eosinophils are granulocytes. Monocytes and lymphocytes are not a granulocytes. Okay. Believe it or not, there's a couple more things that you should know. Okay, you should know what color they stain. So basophils, here's a basophil. So when you stain blood, you use this stain called Wright stain. Okay, when you stain the basophil, Wright stain is a complex stain. In other words, it has multiple simple stains in it. And basophils attract the blue in the Wright stain, so they stain blue. Eosinophils, as a fact, phil means loving. So this is base loving, and because this blue is basic, the basophil attracts the blue. Eosin is red. So eosinophils attract the red or orange dye. And then neutrophils attract both of them. They attract both blue and the orange dye, and consequently they stain a lilac color. So here's blue, okay. Then we have red, orange, and then neutrophils are supposed to be lilac. Lilac. A mixture of both the acidic and the basic dyes. Okay. All right. Let's see. It's important to know that neutrophils and eosinophils can carry out diapedesis. Keep that in mind. We're going to go into that in just a second. Okay. All right. Let's move on to this area. Okay. So here's the author underlining or accenting what I have already said. The fact that lymphocytes can be part of the adaptive immunity as T or B cells, or they can be part of the innate immunity as natural killer lymphocytes. Okay. Then the other granulocyte are monocytes. And something that's important for you to remember if it's in red, it's important, is that monocytes have a tendency to differentiate a little bit depending on which tissue they have. So every tissue in your body has a different version of the monocyte. So in the lungs, for example, monocytes differentiate into alveolar macrophages, okay? And in the brain, they differentiate into microglial cells. And you can go tissue by tissue in the body and you're going to find a different representative of the monocyte, because that is the main guy that's going around and looking for things that don't belong there, okay? So that's important to know. Okay, like I said, I told you that it's important to know what the colors are. So let's look at the basophil. Here's my basophil. This is supposed to be blue. Eosinophil, red to orange. Neutrophil is supposed to be lilac. And if you're looking at that, you're going, that's not lilac. Don't yell at me. That's what the textbook says. Okay, you can look at more than one source. They typically say that. And then the lymphocytes are a gray blue, and monocytes are also a gray blue. Monocytes are significantly larger, and they have this characteristic horseshoe nucleus. Okay. What else should you know as a nurse? You should know a relative abundance. Okay. And relative abundance can be conveyed in one of two ways. This is one of them, by telling the audience what percent of white blood cells it consists of. So, for example, basophils are only 0.5 to 1% of white blood cells. Eosinophils are 2 to 4. Neutrophils are 60 to 70. So, if you're looking at a stain of blood, you can be pretty sure that you're going to run into quite a few neutrophils and very few basophils. Here's lymphocytes at about 0.25%. Monocytes at 3 to 8%. My experience is that it's higher than that, but does the textbook average, okay? The other way to address this is number of white blood cells per thousand or per million, okay? So they give you a proportion. Anyways, relative abundance is important to know. This reminds me of a point, though. Eosinophils are supposed to be pretty rare. So if you're looking at somebody's blood and they're having a lot of eosinophils, it doesn't mean that they have parasites. Chances are is that they're just having an allergic attack. So people that are having an allergic attack typically end up with what's called eosinophilia, which is an increased amount of eosinophils. Okay. We're going to go through the stages of phagocytosis. Okay. Like I said, we have 3 phagocytes in the white blood cells. And why is this important? This is important because these phagocytes not only consume these foreign invaders, but like I told you, they break them apart and then they carry out antigen presentation. And that antigen presentation is an essential precursor to launching the adaptive immune response. So hallmarks of the innate immune system that we're studying right now is that its effect is broad but fast. In contrast, if the adaptive immune response is very specific but very slow. Okay, so it's important to understand that the innate immune system, in its speed and how quick it is, launches the adaptive immune response. And if it wasn't for the speed of the innate immune system, we would be waiting forever for that adaptive immune response to take place. So here's phagocytosis. Like I said, at the very end, we're going to end up with antigen presentation. Your author's calling it elimination here. So what's going to happen? What's the first step? Well, the first step is that you have an infection, okay? Viral, bacterial, whatever. When this happens in your tissues obviously are not happy about it. So they start sending chemokines, okay? Chemokines are a chemotactic factor. What? Well, let's talk about what chemotaxis is, okay? Taxis, if you have positive taxis, that means that you're moving towards something. If you have negative taxis, it means that you're moving away from it, okay? In chemotaxis, you're moving towards a chemical gradient. In negative chemotaxis, you would be moving against that chemical gradient. So in chemotaxis, the white blood cells are moving towards a chemical gradient. What is that chemical? They're chemokines. They're a chemotactic chemokine that causes the cells to follow that chemokine to the source of the infection. That's one way to do it. Another one is complement. Complement can make peptide fragments, proteins, that also function as chemotactic chemokines and attract the white blood cells to the source of infection. Finally, the microorganism itself will release substances that attract the white blood cells. So the very first step is called chemotaxis. Again, the attraction of the white blood cell to the site of infection as it follows this chemical trail. And again, these chemical trails are important, otherwise they wouldn't be in red. What else? Well, after chemotaxis, remember the white blood cells are in the circulatory system. And the infection is in the tissues. So imagine that you're in a highway, and then on the side of the highway, it's a problem that you need to attend to. You have to go from going 65 miles an hour to standing still like that, so you can move from the circulatory system to the site of infection. That doesn't sound like a simple task. So how do we do it? Well, we end up with this event where the epithelium literally makes receptors, little hands, to grab onto the white blood cells that are coming to help, okay? That event is called margination, okay? So in margination, why margination? Because the white blood cell is moving towards the margin or the side of the vessel where there's a little receptor ready to grab a hold of it, Okay, so that's margination. Here's a white blood cell, and it goes to the margin, and it gets caught. So that's margination. Once it gets caught, now this white blood cell has to do something very strange. It needs to go from being an inactive little white blood cell to a cell that needs to move through the tissues through amoeboid motion so it can go after the bad guy. Okay, that event where it traverses from the aqueous environment of the blood to the solid environment of the tissues is called diapedesis. Okay, dia means two, ped means foot. So effectively, you're telling everybody that this thing has grown 2 feet. Yep, pretty much. Diapedesis is grown feet, and now it's going to move through these pseudopodia, these false feet, through the tissues in order to find the site of infection. So chemotaxis, margination, after these two, margination, diapedesis, now is in the tissues and it finds the bad guy. What does it need to do? It needs to attach to the bad guy. That's called adhesion, okay? Remember, if you can't adhere to the bad guy, you can't grab it. We talked about this when we talked about waxy walls or cells that have a thick glycocalyx that is particularly slippery. If that's the case, then the phagocyte has a hell of a time grabbing onto that organism, and it might not be able to phagocytize it, okay? So one of the events that has to happen is called adhesion, which is where the phagocyte literally makes a receptor and it grabs onto that bad guy, okay? That's adhesion. Now what? Now the phagocyte wraps around the bad guy, okay? And that becomes ingestion. When it gets ingested into the phagocyte, it is in a vacuole called the phagosome. So nothing has happened. The only difference is that now that the bacteria is not outside, it's inside the phagocyte, and it has been ingested into a phagosome. Now that bacteria, virus, whatever it is, needs to be broken down into small pieces. That is carried out by a lysosome. So you have a phagosome with the bacteria, and you have a lysosome with all the enzymes necessary to kill this guy. And these two need to come together so that the enzymes can be released in order to kill the bacteria. That coming together of the phagosome and the lysosome is called maturation. Maturation. Once those enzymes have destroyed that bacteria or that virus, that is called killing. And once that opponent, that foe, has been destroyed into very small pieces, those pieces can either be released to the environment or they can be presented as an antigen, and that's called elimination. So if you want to see the author's picture of this, it shows all the events here, chemotaxis, adhesion. So feel free to look at this picture at your own leisure. Okay, but those are the steps of phagocytosis. Okay, we're going to talk about DNA. Let's see. Let's take a second here. All right. So this is a relatively new discovery, probably within the last 6 years or so, and that's the fact that part of the protagonist of the immune system actually use DNA to kill their prey. So eosinophil is one of them. Okay, the other one is why is my thing not functioning here? And the other one is neutrophils. Okay, this is very, very neat. So what's happening? Well, an eosinophil, to recap, is the guy that goes after parasites. So if you have a parasitic infection, you're going to end up with eosinophilia. You're going to end up with a whole bunch of eosinophils in your blood. They're going to go through attempt to go through the stages of phagocytosis, which means that it's going to try to go after the bad guy It's going to try to engulf it. It's going to try to kill it. If the bad guy is too big for the eosinophil, because remember, a parasite is a worm and it can be very large, the eosinophil can therefore attach to the bad guy and carry out degranulation. Okay, remember, eosinophils. Here's eosinophils is one of the granulocytes. So those granules are full of enzymes that are necessary for destroying a parasite. Okay, so it'll grab onto the bad guy. It'll degranulize. It'll carry out degranulation. The granules will come out. The enzymes will be released, and it will try to kill that parasite. Okay. I got to tell you, the enzymes that get released by these eosinophils, they're not very specific. They kill anything that's around. So this eosinophil is not going to have much of a life left. Okay. Once it degranulates, it has very few moments left. Well, so what? The so what is that in its last moments, what it does is it lyses, it breaks up its own mitochondria. Okay, the mitochondrial DNA and proteins come out and form a net to catch the parasite, and something sensational happens. The mitochondria, when they break, they release their cytochromes. Remember, cytochromes are part of the electron transport chain found in mitochondria. Well, it turns out that when one of the cytochromes, called cytochrome C, is released, this thing assembles itself into this huge war machine, into a super destructive machine called the apoptosome. Okay, this is what it looks like. I just Googled it so you guys can see it. Isn't that beautiful? The apoptosome. You can see what it. You can see how to spell it right here. Apoptosome. So if you don't remember, apoptosis is cell suicide. Some means body. So the mitochondria, when it breaks, it makes this huge killing machine called the apoptosome, and it's supposed to kill the eosinophil. But again, this guy doesn't care. All it knows is that it's there to destroy everything around. So while the DNA is holding the parasite in place, the apoptosome is functioning to destroy as much of the parasite as possible. That's incredible. So this means that even in the final throes of its life, the eosinophil is doing everything that it can to protect us. That is incredible. The neutrophils do the same thing. The only difference is that with neutrophils, they don't use mitochondrial DNA. They actually use chromosomal DNA, and they actually generate proteins, fibers, and together they form neutrophil extracellular traps, or nets. Cute, right? Nets. And again, with neutrophils go after bacteria, eosinophils go after parasites. So the neutrophils hold these bacteria in place, and then the mitochondria do their thing, and they end up helping destroy the bacteria. Very, very neat. Okay, remember that lymphocytes can also be turned into natural killer lymphocytes, NK cells, okay? That's part of the innate immune system, which is beautiful because it happens quickly and it protects us quickly. What do you need to know about this? You need to remember the natural killer cells destroy cells in your body that are infected with viruses, or if they don't recognize a cell because their surface proteins are not recognizable, like in a cancerous cell or a tumor, it will destroy those as well. So imagine NK cells are there to protect us against the flu, and they're there to protect us against cancer. Incredible stuff. Beautiful things. Okay. It's not in red, but I've got it bold. This means it's important, even if you're not going to be assessed on it. So toll-like receptors, okay, these are important because these only happen in the innate immune system. And what happens, guys, is that us and bacteria, we've been doing this do-si-do for 3.8 billion years, the entire time that we've been here on this earth. So we've grown to know each other very, very well, okay? So the cells of the innate immune system, okay, have receptors called toll-like receptors that recognize what's called pathogen-associated molecular patterns, PAMPs. In other words, these are things that are commonly found in bacteria that are constantly causing infection in our body, okay? And when this happens, all right, what do our white blood cells do? They mediate inflammation, they stimulate the adaptive immune response, and they carry out apoptosis, like we just mentioned. Cell suicide, but also suicide of the bacteria or the parasite. Why do we care? We care, guys, because, as I said before, the hallmark of the innate immune system is that it is broad in spectrum but fast. And the hallmark of the adaptive immune system is that it is very specific but slow. Now we have learned that the innate immune system is not only fast, it is also specific, because it can recognize these common pathogen-associated molecular patterns. That's fantastic. That means that within hours, not days or weeks, but within hours, our innate immune system is protecting us against these common invaders. This chart shows some of the pathogen-associated molecular patterns that we look for. They could be gram-positive peptidoglycans. They can be lipoteichoic acid, etc. Each toll-like receptor is specific to a set of pathogen-associated molecular patterns. I'm gonna move through nods here. Okay, interferons. What does an interferon do? I tried this in lecture yesterday, and people got upset at me, but I'm gonna do it anyways. So here it goes. I tell people that interferon is like a fireman. If your house is on fire, you're in trouble, because the fireman is not there to put your house out. They're there to protect everybody else's house. Okay. Why am I saying that? Because that's the way that interferons work. Okay. Here's my virus. Here's my infected cell. It's going to go into this infected cell. The viral particle uncoats. I'm going to make this larger so you can see it. The viral particle uncoats. It goes in. There is it's RNA. Its RNA gets turned into DNA, and then the DNA gets turned into messenger RNA. And when this messenger RNA is found in the cytosol, as I've said many, many times, our cells do not like genetic material in the cytosol. Your cell starts creating interferon. Okay. Now, what happens to the infected cell? It dies. It dies. All those viral particles multiply, and the cell lyses. However, what happens to the surrounding cells? Well, that interferon goes to the surrounding cells, and it causes the expression of inactive antiviral particles. So now, if this cell becomes infected, okay, there'll be viral encoding, there will be production of DNA, but these inactive antiviral particles will become active in the presence of the viral RNA, and it will associate with the ribosome and prevent translation of the viral proteins. The infection has been arrested. Okay, so that interferon did not protect the original cell. It did, however, protect all the cells surrounding that. So when you're talking about people that are infected with HIV, interferon happens to be one of the things that are added to the cocktail. What else should you know? You should know that gamma interferons are also responsible for stimulating the phagocytic activity of macrophages and neutrophils. So not only do they protect the cells, not only do they attract phagocytes, it actually activates them. And the main ones that they're activating, again, you should remember, are macrophages and neutrophils. Okay. All right. Now we're going to talk about complement. Big picture. Big picture. What does complement do? Here's complement cascade. And complement means that it complements the immune system. It's another branch. Okay. One of the main things that complement does is it makes these MACs, membrane attack complexes. And when it does that, it makes pores in bacteria. Look at this pore bacteria. We want to call it pore. So here's a transmission electron micrograph of a bacteria with all these pores. This bacteria is dead. And all those pores is the end of a cascade of the complement cascade. Okay. So that's how complement works. It also functions chemotactically. Chemotactically means that it functions as a means of attracting additional phagocytes to the site of infection. It also functions as a mediator of inflammation. So in that case, it's helping basophils and it's helping other mediators of inflammation. Okay. So now that we know what it does, how does it get activated? Well, we've known for a long time that it gets activated through what's called the classical pathway. Okay. Classical means that it needs an antibody. And this is a problem, guys, because you have the innate immune system, which is what we're covering right now. And then the innate immune system launches the adaptive immune system. The adaptive immune system means that it's going to activate T cells, and then it's activating B cells, and then the B cells are going to make antibodies, and then finally the antibody is going to launch the cascade. Oh my gosh, how long is this going to take? Forever. Okay. So imagine our surprise when we found out that complement gets launched very quickly. Well, if that's the case, then there has to be something other than this classical pathway. Okay. And there is. There's the alternative and the lectin pathway. So in the alternative pathway, one of the proteins of complement, C3b, okay, the lowercase b means that it's part of a dimer, okay? When it breaks, it becomes a lowercase b. So that C3b, if it recognizes a pathogen, then it launches complement without having to launch the adaptive immune response. Fantastic. We're protecting ourselves quickly and in a very strong way. Finally, some bacteria have surface sugars such as mannose that is recognized by our body via these lectins. And when that takes place, that launches complement as well. Okay. So there's three ways: classical, alternate, and pectin. The classical is the slowest way of doing it. Okay. It requires the adaptive immune response. The alternate and lectin pathway means that the complement cascade can be launched in a matter of hours. So it is fast, it is specific, and it is lethal. Okay. And that's it for this chapter. Thank you.